I think the most pressing problem in some senses we face in the modern world is figuring out how to build things that are becoming increasingly complex. We've spent 5 decades educating young engineers in reductionism, that they should learn more and more about less and less and really understand the fundamentals of the science underneath engineering. And it actually ill-prepares them to go out and build very complex systems. Why are things becoming more complex? It's just mostly market forces. You used to have a Xerox machine with a button that you push to copy, and now you have a Xerox machine with tens of controls to adjust the tone and the orientation and whether it's stapled and whether it's collated and so forth. I can actually remember, this is a true story, one Saturday morning when I was on the 9th floor of NASA headquarters with the administrator, and he and I were working quietly on a presentation, and we needed a Xerox copy. And at this time I was the head of the Aeroastro department at MIT. He was the NASA administrator. So we went into the copy room where we were presented with this industrial strength copier, and between the two of us we couldn't figure out how to turn it on. And we sort of course looked at each other and said, we have the senior-most academic in the country in space and the NASA administrator, and we can't turn on the Xerox machine. Who are they making these things for? So the need to put more features and more capability and more performance and the networking of all of our systems together to build systems of systems is creating this enormous issue of how we reason about complex systems, and particularly when we have to craft them and build them and assure their performance over their lifetime. So that's actually the area in which I do research, which we call system architecture, the product development of complex systems and products, where we start at the stakeholder engagement to try and understand in these very complex situations, like we're building a new refinery on the border of one state and another. So how do you deal with the stakeholders in one state and stakeholders in the other state, the downstream developers of the refinery products and so forth. Then we do extensive conceptual exploration, and this is numerical. So we actually have figured out how to encode the genome of a concept into a mathematical programming so that we're able to explore not only a design space but a conceptual space. Would you transport people with a car or a boat or a plane? Not only how many wheels the car has. So we've developed techniques and design environments in which this type of high-level decision-making can be supported. And fundamentally, it's about supporting decisions. You have to recast the problem into the decisions that the decision makers will eventually make. And when you do it this way, it becomes much simpler for the decision makers, whoever they are, to be able to understand and reason through the complexity. If I choose this, I get this result. If I choose this, I get this result with the appropriate cost and benefits that are associated with them. So the research program, which we call the System Architecture Lab, is looking at techniques and processes and tools to support decisions about the crafting of these very complex systems of all types, electronic, informational, mechanical, biological. There are no differences amongst the ways we treat these systems, so that we're able to be Catholic, that is, say we can apply these tools to all types of problems, and we can apply them, most importantly, to problems which transcend traditional disciplines.